So here we have 2015, October, November, paper 21, question number 3. Heptane, C7H16, that's the molecular formula, is an undesirable component of petrol as it burns explosively, causing knocking in an engine. There are 9 structural isomers with the formula C7H16, only 2 of which contain chiral centers. Explain the meanings of the terms structural isomers and chiral. Structural isomers are compounds with the same molecular formula but different structural formulae. Okay, compounds with the same molecular formula but different structural formulae. Different structural formulae. All right, next, what is a chiral carbon atom? A chiral carbon atom is a carbon atom, okay, a carbon atom that is bonded to 4 different atoms or groups of atoms. Okay, that is bonded to 4 different atoms or groups of atoms. Obviously, it's tetrahedrally bonded to 4 different atoms or groups of atoms, right? So this carbon atom is only making single bonds, okay, 4 different atoms or groups of atoms. Okay, and chiral carbon atoms are asymmetric, okay, they don't have any line of symmetry. Give the structures and names of the 2 structural isomers of C7H16 which contain a chiral center. So we have to draw the structural isomers, of C7H16 that have a chiral center. Now obviously the straight chain isomer, which is heptane, doesn't have a chiral center because we only have CH3s and CH2s. So here's heptane, right? It's CH3, CH2, 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 and then CH2, CH2, and then CH3. Right? So we have 7 carbon atoms, and each of the carbon atoms is bonded to at least 2 hydrogens. So it definitely doesn't have a chiral center. So we know that the straight chain isomer, right, doesn't have a chiral center, so that's not the answer. It has to be a branched isomer. Okay, it has to be a branched isomer. So let's say we had a 6 carbon chain. Okay, let's say I had a 6 carbon chain. 1, 2, 3, 4, 5, and then 6. Now, if I put a branch, let's say on the second carbon, so I have a methyl group on this carbon, will I have a chiral center? Obviously we can't have a branch on the ends because then that would just be a 7 carbon chain. But if it was on the second carbon, would it be a chiral center? So let's say if I had a methyl group here, would there be a chiral center or would I have a chiral center? So we don't have any chiral center here because this carbon is bonded to 2 methyl groups. Again, I haven't shown the CH bonds yet. Okay, so this is not a chiral center because this carbon atom would be bonded to 2 methyl groups, and then again all the others would just be CH2s and CH3s. Okay, so that's not a possibility, right? So we can't have a methyl group on carbon number 2, so not here or here. What if it was on carbon number 3, so this carbon or this carbon, either one? Then would I have a chiral center? Now I would have a chiral center, right? This carbon atom would be bonded to a hydrogen, right? It's bonded to a methyl, an ethyl, and a propyl group. So it's bonded to 4 different atoms or groups of atoms. So here I have a CH3, CH2, and then a CH3 here. Then I have a hydrogen obviously on this carbon because each carbon is making 4 bonds, right? 4 single bonds. And then I have a CH2, CH2, and then CH3, right? So now I have a chiral center here. This carbon atom is a chiral center, right? It's bonded to 4 different atoms or groups of atoms, right? Methyl, ethyl, and propyl, and then a hydrogen. So over here we have a 6 carbon chain and a methyl group on carbon number 3. Okay, so this is 3 methyl hexane. Okay, 6 carbon chain, methyl group on carbon number 3. So 3 methyl hexane. So now this is the only possibility that has a chiral center where we just have 1 carbon atom in the branch, right? The methyl group can either be on carbon number 2, right? In that case, we don't have a chiral center, or it can be on carbon number 3. Again, whether we put it on the left or the right, doesn't matter. If the methyl group was here, then this would be carbon number 3, right? It would still be 3 methyl hexane. Now let's look at possibilities where we have a 5 carbon chain and we have 2 carbon atoms in the branch. Okay, so let's say I have a 5 carbon chain, right? I have a 5 carbon chain like this, and let's say that I have a methyl group here and a methyl group here. That's one possibility, 2 methyl groups next to each other on carbons next to each other. Over here again we have a chiral center. It would be this carbon atom, right? This carbon atom would be bonded to this carbon atom here, carbon number 3 would be bonded to a hydrogen, a methyl, an ethyl group, and then this 3-carbon group here, right? So this is our chiral center. So again, we have to draw out the hydrogen. So we have a CH3 and then a CH bonded to another CH3 in the branch. And this is also a CH3, and then this is a CH2, CH3. Okay, so this is our chiral center here, right? This carbon atom. So this is 2,3-dimethyl pentane. We have a 5-carbon chain, so that's pentane, and we have methyl groups on carbons 2 and 3. So the name is 2,3-dimethyl pentane. Over here, when the question says give the structures and names of the 2 structural isomers, right? When we say give the structures, any valid structure, okay, is acceptable. So you can draw the skeletal structure for these compounds. Okay, you can just write down the structural formulae. We can also just write down the displayed formulae, okay, or draw the displayed formulae where we have to show every single bond, okay, but that would also be a valid representation. Or we can draw this guy, which is somewhere in between a structural formula and a displayed formula, okay. Any valid structure is acceptable. Write an equation for the complete combustion of heptane. Okay, for complete combustion, we can use molecular formulae. So we have C7H16 reacting with oxygen to form carbon dioxide and water, right? Let's say we just have 1 mole of heptane, then that would mean we have 7 carbon atoms on the left. So we'd have 7 CO2, 7 carbon atoms on the right. Then we have 16 hydrogens here. So we'd have 8 H2O, right? And then we have 7 times 2, which is 14, plus 8, which is 22 oxygen atoms. So that would be 11 O2. Write an equation for the incomplete combustion of heptane leading to the production of a solid pollutant. So a solid pollutant that's a result of incomplete combustion is carbon, right? When incomplete combustion, instead of carbon dioxide, we can either get carbon monoxide or we can get carbon, right? Or soot. So over here, since they're asking for a solid pollutant, that'll be carbon. Okay, it's just a black powdery solid. So we have C7H16 reacting with oxygen to form carbon and H2O. Okay, so again, we have 7 carbons on the left, so we'll have 7 carbons on the right, and then we have 16 hydrogens on the left, so we'll have 8 H2O, and then we have 8 oxygens on the right, so we'll have 4 O2. Right, so incomplete combustion takes place when we have a lack of oxygen, or we have a relatively smaller amount or a lower amount of oxygen available. Incomplete combustion can also lead to emission of unburnt hydrocarbons. State one environmental consequence of this. Now, unburnt hydrocarbons, okay, unburnt hydrocarbons can react with oxides of nitrogen to form peroxyacetyl nitrate, okay. Peroxyacetyl nitrate, also abbreviated as PAN, P-A-N, peroxyacetyl nitrate. Now, this is a component of photochemical smog. Okay, so unburnt hydrocarbons, one of the major environmental consequences is that they react with oxides of nitrogen, okay, and they can lead to the formation of peroxyacetyl nitrate. Okay, peroxyacetyl nitrate. Okay, which is basically a component of smog. Okay, photochemical smog. The reaction of heptane with chlorine in the presence of UV light produces a wide variety of products. Formation of the monochloroheptanes can be represented by the following equation. Name the mechanism of the reaction between heptane and chlorine in the presence of UV light. The name of the mechanism by which heptane reacts with chlorine is referred to as free radical substitution. Okay, free radical substitution. Describe this mechanism using suitable equations and including the names of each stage in the process. The first stage of the process in free radical substitution, okay, is initiation. Okay, in initiation, what happens is that a chlorine molecule breaks down to form 2 chlorine radicals. So we have homolysis or homolytic fission of the Cl-Cl bond, and this homolytic fission results in the formation of chlorine atoms. Okay, these chlorine atoms are free radicals. They have an unpaired electron, right, in the neutral species. The next stage is propagation. Okay, it's propagation, and what happens here is that the chlorine radicals will now react with heptane. Okay, the chlorine radicals will now react with the C7H16. Okay, now over here, since they've shown it in the molecular formula form, right, they've shown it as C7H16, we can write it down as molecular formula. If it's not shown this way, right, for something like ethane, for example, if they showed CH3, then we would have to write down structural formula. But here, since they've given the molecular formula, we can write it down in this way. Okay, so what will happen is that the chlorine radical will react with C7H16. Okay, chlorine radical will react with C7H16. The CH bond breaks, okay, and HCl forms. CH bond breaks, HCl forms. So what we get here is a C7H15 radical, right? Because the CH bond breaks homolytically again, okay, and then we get HCl. And then the C7H15, right? This alkyl radical can react with another chlorine molecule. It can react with another chlorine molecule, and we're going to end up making the monosubstituted product. So that'll be C7H15Cl, okay, and we're going to get more chlorine radicals. Okay, initiation, we get radicals from the chlorine molecule. Okay, so molecule is converted into radicals because of the homolytic fission or homolysis of the Cl-Cl bond. Propagation, the radical reacts with the molecule to give you more radical in molecules. Okay, and then same thing here, radical reacts with molecule to give you molecule and radical. Now this C7H15 radical can also react with other radicals at the same time. So it can react with other chlorine molecules, it can also react with other radicals. Okay, and that stage is referred to as termination, right? When two radicals react with each other to form a molecule. So in the termination stage, what will happen is that the C7H15 radical can react with a chlorine radical to form C7H15Cl. Okay, there are other terminations possible as well. So for example, two of these C7H15 radicals can react with each other as well. So I'll write that down as an alternative termination over here, right? C7H15 radicals can react with other C7H15 radicals, okay, to form C14H30 as well. Okay. But this is your mechanism, right? You have the initiation stage, you have these two propagation equations, then you have the termination equation, and you have to clearly name each of these stages.